Hello class, and welcome to Chapter 3, which is going to be all about linear functions. Today we're going to talk about relations and functions, and this is section 3.1. By the end of today's lesson, you will be able to identify domains and ranges and determine reasonable values for both of those concepts. You will be able to identify functions and identify the constraints on the domain. So to start this lesson, it's going to be very vocabulary heavy. This is going to be important for us as we move throughout the rest of the chapter. So there is going to be a lot of vocabulary at the start of this lesson, and you're going to want to make sure you understand these concepts. If you do not, please make sure you are asking questions when you get to class so that I can clarify things for you, because it is very important that we understand these terms. So first, a relation is a set of ordered pairs. So any list of any points that can be put onto the graph. A function is a specific type of relation where each input, when we're talking about inputs, we're talking about x values on a graph, is assigned exactly one output, which on a graph is going to be y values. Those inputs and outputs also have specific names. The inputs are the domain. Again, these are the x values. And your range, your outputs, are your y values. So another way you could read this definition of a function is a relation where each member of the domain is assigned exactly one member of the range. So I've got 4 different sets of relations down here, 4 different lists of ordered pairs, kind of to help us interpret what a function means. So 1 is paired up with 2. That means 1 is assigned to its own unique number, which is 2. Then we've got 9, which is paired with a unique number 8, 7, which is paired with a unique number 6. This is a function. This second group, I have my first 3 points the same, so I've got a function up to here, and then I have the point 1, 2. We already used 1, and it was paired with 2. Since this is just a repeat of that first pair, it is still a function because the number 1, that input of 1, has still only had one output value, which is 2. Then we come to another option. Those first 3 points, again, still the same, so that's a function. And now we have the number 5, which has been assigned to the number 2. 5 is a new number, so it is okay that it is assigned to 2 because 5 has been assigned its unique number now. So every time we see 5, it would be paired with 2. This last one, again, first 3 points are the same, but now this last point says 1, 5. We already had a 1, and it got paired with 2. So 1 is not allowed to be paired with 5. So this is an example of something that is not a function because we had a member of the domain that was paired with 2 different y values, 2 outputs as opposed to just 1. Couple more terms that we have specific to the domain. So the domain is continuous if the inputs can include all real numbers. That means whole numbers, negatives, decimals, fractions, repeating decimals, irrational numbers. So any possible number that you can think of can be part of a continuous domain. When you graph something that's continuous, it's going to form a straight line or a continuous curve. Everything is going to be connected. Some examples of things that might have a continuous domain are if you're talking about time, because you can have fractions of time. If you're talking about money, you can have parts of a dollar. If you are talking about distances, you can have pieces of a mile or a whole mile. So all of those things where fractions and decimals are okay. Our second option for the domain is called a discrete domain. This happens when the inputs only include whole numbers or integers. So our inputs cannot have fractions or decimals, and the graph is a series of disconnected points. So they're not connected to each other. Each point is separate. So think of things like if you are surveying an amount of people, each person would be its own element in the domain. You could not have those connecting. So you have to have whole numbers there. Or if you were counting the number of cars, for example, you have to count cars as a whole. You're not going to count a half of a car. So anything where you have to have whole numbers or numbers that are both positive and negative, but no fractions or decimals, then we call it discrete. Last piece of vocab we have is called a mapping. And this is an illustration of how each element in the domain, again, that's our x values, is paired with the elements in the range. That's our y value. In order to set up a mapping, the first thing we need to do is list our x values, and then we also need to make a list of our y values. When you do this, you need to make sure that they are in order from least to greatest. So when we're looking at our x values, we've got 1, 4, 5, -1, and -2. So I'm going to start with -2, then go to -1, and then we've got 1 and 4 and 5. Then we come over and we have our list of numbers in the range. So 2, 5, -2, 5, and -2. Notice some of those numbers repeat. If you have a number repeating, whether it's in the x or in the y, we only list it once. So -2 is my smallest number. Even though it happens twice in the problem, I'm only going to write it down once. Then I've got 2, and then the last one is 5. Again, it happens twice, but I'm only going to write it down once. Now, to finish a map, what you're doing is connecting the points that go together. So -2 is paired with -2. -1 gets paired with 5. 1 gets paired with 2. 4 gets paired with 5. And 5 gets paired with -2. So it shows you how each point in the domain connects to its value in the range. So in this case, if we look at this, this does illustrate a function. Each number in the domain only has one arrow going out, so each number is going to its own answer. Some of the answers are repeated, but each number can only connect to one answer. So one of the parts of this lesson is going to simply be identifying the domain and range. When you do this, just like we did on the last slide, you're going to put them in order from least to greatest, and you're only going to list it once if there's a repeat. So for example, here in our domain, conveniently they're already in order for us. We use squiggle brackets, which if you are typing this on your computer, you hold Shift and then the button next to the letter P. And then to get the other one, it's the button next to the right of it. So that's how we get those squiggle brackets, by holding Shift and the button to the immediate right of P. So we've got our domain is -3, -1, 1, 3, and 4. Then we've got to list our elements in the range, which again, starting with our smallest number, is going to be -5. Then -2. Again, we only list it once, even though it shows up twice. And then 1, and then 3. So we use those brackets, those special brackets to indicate that it's a set of numbers, and then we label them domain and range so we know which one is which. Go ahead and try this one on your own. And you can see the domain and the range, and you should again have those squiggle brackets listed around them. Another thing we can do with domain and range is talk about reasonable ideas for the domain and the range. So for example here, a restaurant needs to order chairs for its tables. One table can accommodate 4 chairs, and then we want to know if this situation is continuous or discrete. So our first job is going to be to decide what's the domain and what's the range. What are we inputting and what are we getting out? In this case, our domain is going to be the tables. The restaurant is going to have to pick out how many tables it wants, and then once it makes that decision, the range, the chairs, is going to be a result of that. They don't buy the chairs first and then fill in the tables. They buy the tables and then they fill it in with chairs. So whatever you're picking, whatever is determining the situation is that domain. So if we're talking about the domain here, now we have to think about what kind of numbers could work for tables. Obviously, we aren't going to have negative numbers. So we are going to start at 0. And then we can't have fractions of a table. So what we would say for this is whole numbers. Remember, whole numbers means starting at 0, going up with no fractions or decimals. Whole numbers from 0. And then since it doesn't give us how big the restaurant is, you can just say to maximum capacity, or until as big as they can get, or until they're full. Something along the lines to say you start at 0, you're counting by whole numbers, and it's going to keep going until they can't fit anymore. The range then, we have to talk about possible numbers of chairs. Again, if we have 0 tables, then we're going to have 0 chairs. If we have 1 table, we're going to have 4 chairs. 2 tables, 8 chairs. 3 tables, 12 chairs. So again, we're dealing with whole numbers. There's no fractions, there's no decimals, and we're starting at 0. So we're starting at 0, from 0, and then we were getting bigger, so from 0 and up, by multiples of 4. Or by counting by 4s, or by going up by 4. Something to indicate that every time you go up, you have to make a jump of 4 chairs, aka 1 more table. So we can't just say whole numbers from 0 up, because you're not just going to order 1 chair. That wouldn't work for a whole table. So you have to, in this case, indicate that you are counting by 4s. So when you're reading the problem, make sure you pay attention to what the domain is, what the range is, and then you have to think through logically how you can figure out what numbers might work for the domain and range. The last thing this question asked us is whether it is continuous or discrete. Since we're looking at just whole numbers, we can't have fractions or decimals, this is going to be a discrete function. Remember, that means we can't have fractions or decimals. Go ahead and try this one on your own. When we're looking at this problem, again, first thing we want to do is identify domain and range. So the hose is filling it up. As we are counting, the amount of time is determining how full the pool is. So our time is the domain, and our gallons is the range. So our domain, we can have fractions of time, so we got real numbers starting at 0 until the pool is full. And our range is also real numbers. We can have fractions of gallons between 0 and 10,000, which is the limit when the pool is full. This is a continuous function because we are allowed to have fractions or decimals. Next thing we're going to talk about is being able to identify functions. There are 3 different formats in which you could see a function: listed out as ordered pairs, listed out in the map, which we talked about, and then in a graph. When you're looking at the ordered pairs, you want to make sure you start by looking at your x values. So we have x values. We've got 1, 5, 7, and 8. Those are all unique x values. So since there's no repeats, it's definitely a function. And then again, because there's no repeats, we're going to go one step further, and we're going to say this is a one-to-one function. An example of something that is not a one-to-one function would be if I added on the point 9 and paired it with -1. Our 9 and our 7 both go to -1, so each x doesn't have a unique y, but each x has a y. So this function is a function, and it is one-to-one. Right here, we've got a map. We're looking at each specific element of the domain. Each one goes to a single number in the range. There's only one arrow coming out of each number. So once again, this is a function, but this time 1 and 2 point at the same number. 4 and 5 point at the same one. So this is not a one-to-one function. Each x can go to the same y. So we can have more than one x paired with the same y. Again, each x only points at one number, but some of the numbers being pointed at get repeated. The last thing down here with our graph, there's a nice little trick called the vertical line test. What the vertical line test means is that if you take a vertical line, so this blue line right here, and you drag it over the graph, it can never touch your graph more than one spot at a time. So right here, each time I drag this blue line over the top, it only is hitting the red line at a maximum of one time as I drag it over. If I were to draw in a second graph, for example, if I put this green one right here, and I did the vertical line test again, the green one would not pass because right now it's hitting at 1, 2 points. So if you draw a vertical line and it hits it twice, it does not pass the vertical line test. But if we go back to our original function, this red line, it is a function because it passes the vertical line test. So again, if you have a graph, you can use the vertical line test. Go ahead and try these two on your own to determine if they are functions or not. A is not going to be a function. If you look at our map, we have 3 pairs with 6 and 3 pairs with 7. So that is a repeat of x's with a different y, so it is not a function. If we come over here, each of our x values is different. So we're going to have a function, and it's going to be 1 to 1 because each x value goes to its own unique y value. Last thing we're going to talk about, this is similar to the reasonable domain and range portion, but this is talking about specific constraints on the domain. So this is things that the domain cannot equal. So in this first example, Margaret has a monthly closed budget of $50. She maps out the amount of money she spends each month to the number of items of clothes that she can buy. What is the constraint on the domain? So our only job here is to identify the domain. In this case, the domain is going to be her budget. She has $50 to spend. She could spend $10, she could spend $20, but she has a maximum of $50 to spend. So the constraint is going to be $0, she could spend nothing, to $50. That's the maximum she can spend. Anything outside of that range is an unacceptable input or an unacceptable member of the domain. This bottom one, a company charges 75 cents per pound, or charges a 75-cent per pound shipping fee when it mails package. What is the constraint on the domain? So in this case, again, we have to identify what our domain is. In this case, it's going to be the pounds. The pounds change, and that causes the price to change. So we need to think about what is a reasonable number that we could be using for pounds. So in this case, our only constraint is going to be, it has to be above 0. It could be fractions, it could be decimals, but you can't have a package that weighs a negative amount. So it's got to be above 0, and that's the only constraint on our domain. It could be as heavy as you want, so we don't have to put an upper limit here. Go ahead and try this one on your own. In this case, the constraint is that the domain has to be between 3 and 15 miles because the miles determine the amount of time that he runs. So that is going to be our limiting factor, is that he goes between 3 and 15 miles. If you have questions about this or anything else, please let me know when you get to class.